Okay, so I'm ready then.
Great. So Matthew, let me first introduce you to everyone, and thanks for taking here. So next speaker is Dr. Matthew Giordino, and he's invited, joined with Bernoulli Society, and I'd like to thank especially Dr. Tan-Yan Xu from Bernoulli Society on that. So Matthew received his PhD in 2021 from University of Cambridge, and he's now an assistant professor of statistics at University of Turin. And today he's going to talk about nonparametric Bayesian intensity estimation for covariate-driven inhomogeneous point processes. So thank you, Matthew, for your contribution in the webinar, and we are delighted to have you here. So please feel free to start whenever you're ready.
Yes, so thanks a lot for the kind introduction, and also thanks to the organizer for putting up this nice event, and also for the invitation. So what I wanted to present today is some work that I started during my postdoc when I was at the University of Oxford with my postdoc supervisor, Judith Rousseau, and jointly with Alice Kirichenko on sort of estimation for point processes where there are some covariates that determine the occurrence of the events. So let me just give as a overview on the setting. The motivation is that one of the central problems that is studied in the literature for spatial statistics is the analysis of point patterns. So you can think of recording, for example, the location of some events, or maybe the time of occurrences of events, when you want to understand its relation with an important covariate that you can measure. So to start to introduce the setting, we will think of observing a point pattern n over an observation window in space Wn. And then from point process theory, we know that the key quantity driving the occurrence of points is known as the intensity function. This is defined here. It is defined in a formal way as the ratio of the expected number of points around a small neighborhood at each of each location in space divided by the volume of the neighborhood. We can think of this as an intensity that determines the probability of observing one point at each location in space. Now here we are in the setting with covariates. So in addition to the point pattern that we observe on the window, we also assume that there is a divariate covariate Z, which we can measure at each location in the window. And then we link the points that we observe to the covariate by assuming that the intensity function that determines the occurrence of point is itself a function of the covariate. So the assumption is that lambda, the overall intensity, is a function rho of the covariate Z. Now, when rho is unknown, then the clear estimation problem is given observation of the points and of the values of the covariate to try to make inference on rho. Here, just intuition of what type of applications we are thinking about. We don't have we mostly focus on the theory, but as a illustration, I took this very nice picture from a recent paper by Borraio and co-authors, where the problem is try to understand the link between the occurrences of wildfires in Canada and some important covariates here. The covariates are the temperature and precipitation measurements. And so here what I'm showing is that over here on the top, these are the locations of wildfires over a certain region of almost most of Canada here. And here the picture on the bottom is now the temperature measurement across this region. And now the question is, we can see that as also maybe as our intuition tells us that the temperature has an influence on the wildfires. And for example, here on the right, the occurrence of wildfires seems to follow a bit this region of higher temperature that we see here on the right, and across the region we can see the same. And we have other type of applications across different type of subjects, including the geology, ecology and epidemiology, as for example is illustrated nicely in this paper by Budley. Okay, and now for this problem, there is a rich literature that goes back at least 50 years, but so far most studies focus on parametric type models, where, for example, the intensity is modeled as a log linear function of the covariate, and this has been done both in the frequentist and the Bayesian approach. In terms of non-parametric approach, where here we think of rho as being any type of function, so without finite dimensional parameterization, studies is mostly focused on frequentist procedures, where the typical go-to approach is via covariate-based type kernel estimators. For these, the only rigorous study on the asymptotic properties, the convergence properties that we were aware of, is by this paper of Guiontao Guan in the Journal of American Statistical Association in 2008, where he showed that for a kernel type estimator, there is pointwise consistency at each location of the observation window, in under two assumptions that will be important for us as well. So what he considers in terms of asymptotics is the so-called increasing domain asymptotics in spatial statistics, where you observe that you observe a singularization of both the point pattern and the covariate over observation window W, which is increasing in space. So here in this setting, the accumulation of information comes from considering a domain which is larger and larger. And then the second assumption, which underpins the result, is that the covariate comes from the realization of an ergodic random process, in particular of Gaussian type, under which specification the overall point pattern N is a so-called Cox process, a Gaussian Cox process, which is a random point process with random intensity, which is given by a Gaussian process. Okay, so instead of the frequentist approach, here we are interested in the Bayesian approach, in particular the non-parametric one. So what we will do is we will put a prior, as we are Bayesian, we put a prior on what we don't know. The unknown here is the function rho, which determines the intensity. So we will put a suitable prior on function space on it, and then via Bayes formula we will form the posterior distribution, which will be our key element to do inference. And in particular, what we are interested in here is similar to this study that Guan did, to study the asymptotic properties of this procedure and the estimators that we get from it. So here we make the so-called frequentist assumption in the Bayesian setting. We assume that the data are generated by some fixed true function rho 0, and then we regard as our posterior distribution as a random object that depends on this data generated by the ground truth, and we would like to show and study the rate at which the posterior distribution then concentrates around the ground truth generating the data in the increasing domain asymptotic. So as the volume of the observation window grows, as n grows, and just by concreteness, we make the assumption that the volume grows as n. So this of frequentist analysis of Bayesian non-parametric procedures is an area that has grown over the last 2 decades, so since the early 2000s, and has been pursued in many different statistical problems, in particular for intensity estimation of point processes. The first results were in 2013 and considered settings where there are no covariates. So where you just observe the point pattern and you try to infer the intensity from that. The first results are due to Belitzer in 2013, and they derived L2 optimal contraction rates in a setting where the intensity is assumed to be periodic. And this is this is an important assumption for them because it means that observing a point pattern with a periodic intensity over a larger domain means essentially that you are observing n IID copies of the same point pattern, but over a fixed domain. So in this case, just the unit interval. And then once you have n IID observation, what you can do is you can appeal to the general Helling testing theory for posterior contraction rates in Bayesian nonparametrics. And they use this then to obtain their results. And in similar setting, there have been some further results. One by Alice, one of the co-authors of the paper I'm presenting, with Harry van Zanten in 2015, where in a similar setting, so again with NIID observation of the point pattern over a fixed window, they prove L2 contraction rates for a Gaussian process prior. And then more recently by Judith Rousseau with Sophie Donnet and other co-authors, instead of looking at Helling testing theory, they developed an alternative strategy, which is with L1 type test to obtain contraction rates with respect to L1 type metric under smoothness shape constraints for the intensity. And let me also here just briefly show some related results with the one I've discussed, which still, however, only cover the case where you have no covariates and where instead of looking at increasing domain asymptotics, you always think that you have a fixed observation window and you can observe multiple realization of your point processes. Okay, so looking at these studies and in general the literature, really the case with nonparametric Bayesian modeling of covariates depending intensity depending on covariates was unknown. At least we weren't aware of any results. So now I can now start presenting what we did. And maybe I should warn that the next couple of slides will be the most technical, but hopefully I can talk you through them with clarity. But the idea is looking at the theory for contraction rates in Bayesian nonparametrics. The first key feature that you have to understand is the type of metric for which you can construct tests to separate alternatives. So the idea is that you think of the problem of estimating the function rho, in our case, from data n and z, so the points and the covariates. If you fix two alternatives for the ground truth, so say ρ1 and ρ2, this will be separated by a certain distance. And for this distance, you would be able to construct tests with good control on the type 1 and type 2 error, which means that as the distance between the two alternatives gets larger, so in principle, the statistical problem of separating the two of them from the data should become easier. Then you have a quantitative control on the type 1 and type 2 error of your test in terms of this distance. Okay, and so here what we did is we built on the previous result by Judith Rousseau and Sophie Donnet and the co-authors, in the case without covariates, to build tests for alternatives that are separated in an L1 norm. But here, since we have covariates, the L1 norm for which we can construct the test is an L1 norm now on the covariate surface. So it involves the evaluation of the two functions ρ1 and ρ2 over the covariates z. And to do this, we exploit properties of Poisson random variables and the fact that conditionally given the covariates, then the count of events on any set still follows a Poisson distribution. So the precise lemma is this one, and perhaps the details are not so important. But yes, the idea is that given the two alternatives, then we can construct a test. The test for us will just be a measurable function of the data that takes value either 0, in which case you take ρ0 as the alternative that you accept, or 1, in which case you take ρ1. And then you can provide a control on the type 1 error, which is the first equation here. And you can see that it decreases exponentially as the L1 distance between ρ1 and ρ0 grows. And then secondly, you also have a similar control, actually involving the same type of metric for the type 2 error. Okay, so again, here in the exponent, we find the metric with respect to which we can construct the test. And an interesting feature also is the appearance of this factor 1 over n, which simply comes from the fact that we are considering L1 type norms, so integral norms over a domain Wn, which is growing as n. And so as we integrate, we have the volumetric effect of the domain also coming in. Okay, but once you have established the existence of tests for a metric, then what you can do, you can appeal to the general sort of program of Bayesian nonparametrics, which tells you that once you have the test, if you take a nonparametric prior with certain well-understood conditions, then you obtain posterior contraction. And so these conditions are now familiar if you have already seen perhaps results of this flavor. It tells you that you have to pick a prior that pi that puts sufficient mass around ρ0 as quantified by a certain rate of convergence Vn here going to 0. And then you also would like your prior to put most of its mass on a sequence of subset of the parameter space for which you can provide a bound on the metric entropy. And once you have this condition, which let me just remark that these are very well understood conditions for a large class of priors. So for example, Gaussian process prior, but also mixture priors and other classes. We know how to verify this condition and to get a precise rate of convergence Vn. And so if you can verify these three, then in our setting, combined with the testing lemma from before, what you can obtain is that your posterior distribution will concentrate around the ground truth ρ0 generating the data at the rate Vn, which is identified by these three conditions, in this let me call it empirical L1 distance scaled by the volume of the observation window. So this L1 metric for the ρ minus ρ0 over the covariate surface. Okay, so this will be for us the sort of general program that we will try to follow and build on. If we can find priors satisfying this assumption, then we can via this theorem have a first result that has essentially that the average pointwise distance between a sample from the posterior and the ground truth will be small, in particular smaller than in norm will be smaller than Vn. Okay, but still, if we look at this result, now it's still not in the fashion that we would like in to satisfactorily answer the problem of estimating ρ0, because it involves the covariate. So in particular, it is a metric not directly expressed in terms of just the function ρ and ρ0, but it considers their distance with respect to the covariate surface. So what we would like to do next is to go from this theorem into a similar contraction rate theorem, but with standard metric that only involves ρ and ρ0 and not the covariate. Okay, so and this what we do in order to get to this result is really to try to embrace the message that Guan put forth in his paper, where one of the other key conditions to get consistency of the kernel estimator was to assume that the covariate field is itself random and it's ergodic. And here this is key, because if you think of observing an ergodic random field over an increasing domain, then ergodicity will tell you that the covariates will take the same value multiple times over the domain. There is a sort of almost oscillatory behavior, of course, random of the covariates. And so since we are able to observe multiple times the same covariate values, by that we can observe the same multiple times the same intensity values, and this gives you an accumulation of information about the function to be estimated. So this is really the key idea that was behind the consistency result for kernel estimators in Guan, and we can see here the same also in our setting. The observation is the following: that if we look at the metric, the empirical L1 metric with respect to which we have a posterior contraction in the previous theorem, this is an average, so 1 over the volume of the window, and then we have the integral of the difference between rho and rho 0 over the covariate values. But now, if the covariates are ergodic and stationary, then as the domain increases, converges to the all of RD in the end, these averages, integral averages, will converge to integrals with respect to the over the state space of the covariates with respect to the stationary measure. And this is now, if you look at the second line here, this is now exactly the type of metric that we would like to get contraction with. So it's just a standard type L1 type metric that only involves rho minus rho 0 without the specific value of the covariates. So what we can do then, if we can provide a quantitative version of this type of ergodic theorem, where perhaps we can quantify the rate at which this random object on the left converges to this metric, L1 type metric on the right, then we can combine it. We can combine this with the previous general result to obtain a posterior contraction also on this in this non-random, non-Z-dependent metric. Okay, so this is what we then did in the paper. The precise tools are some concentration inequalities for integral functionals of stationary random fields, for which we drew from a large probabilistic literature that studies this type of object. So maybe just to concretize some of the results that we got on for the purpose of this talk, let's assume the following. So let's assume that the covariates, the d-dimensional covariates that we observe, arises from d independent stationary Gaussian random fields on RD. So we have d covariates. Each one of them is determined by a stationary Gaussian random field with integrable covariance, which gives you ergodicity. And then, okay, so if we assume that we know the well, we can actually just estimate from the data. We can estimate perhaps the mean and the variance of these Gaussian random fields. So we can just standardize. And once we standardize, we can maybe apply a transformation to this random field. Here I'm just applying the standard normal cumulative distribution function, so that overall the analysis is done on a covariate that takes value on a compact set, so 0, 1, the unit hypercube in this case, and this also identifies the stationary distribution as the uniform. Okay, but this is just a sort of pre-processing of the data. What we really think is that as in one, the covariates are Gaussian random fields with integrable covariances. Okay, so then we put a prior on, we specify a prior for the unknown function rho 0. This is a function that will go from the state space of the covariates, so the unit hypercube into R, but it's also positive because it's an intensity. So what we do, just we apply a link function. You can think of eta as the exponential. So we are modeling rho 0 as the exponential of a real valued function W0, of which we make a smoothness assumption so that we can get non-parametric rates of convergence. Okay, so then once we have this parameterization, our prior comes from putting a prior on the function W0, of which we take a Gaussian wavelet prior. We could think of other type of Gaussian priors as well. And here for us, Gaussian priors were of interest because are one of the most studied priors in general in Bayesian nonparametrics, but also there are computational routines for applications with point processes where you can use CMC schemes to compute to sample from the possible distribution. So sort of looking at Gaussian priors here was kind of natural as a first study. Okay, so now under this assumption, what we have is that by the integrability of the covariance of the process Z, and this implies ergodicity for the Gaussian processes, what we can obtain now is a sub-Gaussian concentration inequality of the random L1 metric around its ergodic limit. Then, if we also make use of the specific prior wavelet structure, what we can do is we can use a chaining argument to study the supremum of sub-Gaussian processes in light of this sub-Gaussian concentration inequality that we have, to obtain what we wanted from the beginning. So a quantification of the ergodic theorem. So we can give, in essence, this inequality here in probability gives you a sort of intuition that this random covariate dependent metric will concentrate around its ergodic mean at the correct rate Vn already given you by the properties of the prior. So once now we have established this supremum uniform concentration inequality, now we can combine these with the general theorem and obtain our main result for this setting, where under the assumption that I made in the previous slide, so with Gaussian wavelet prior, if the function ρ0 has regularity alpha in the order space, then the posterior distribution will concentrate around ρ0, now on this standard L1 type metric at the rate n minus alpha divided by 2 alpha plus d, which we know to be the minimax optimal rate of estimation for alpha regular function in this problem. Okay, so with this additional construction, with this additional assumption on the covariates, we have now gone from the previous abstract theorem now on a theorem which specifies the rates and shows that Gaussian processes obtain the optimal rates of estimation. Okay, so with that, I just wanted to wrap up and give a summary. So what we studied is the problem of estimating the intensity function of a Poisson process when it's driven by the covariates. We proved that for a stationary and ergodic Gaussian covariates field, wavelet Gaussian priors lead to optimal rates of convergence. And then also in the paper we have other results where we extend this optimality of rates also to other classes of priors of interest. So for example, hierarchical Gaussian or also mixture of Gaussians, in which case we can also obtain adaptation with respect to the smoothness. And then we also study other classes of covariates process that are sometimes found in application. One example is Poisson random tessellation. And then finally, we also have pointwise type of rates, where instead of looking at integral metrics such as the L1 metric, we just look at the pointwise loss, so rho of x minus ρ0 of x. And for this, we use some recent advances for polyetry type priors. So with that, I will just conclude with the references to the preprint. And also, if you will allow me, maybe a shameless advertise that there will be an upcoming postdoc opening at the University of Turin on these thematics in general on Bayesian nonparametrics. And so if you're interested, you are more than welcome then to contact me for inquiries. And thanks a lot for listening.
Great, thanks a lot, Matthew, for the excellent talk. I think we have probably 1 minute if there is any question for Matthew. And if there is any question, I think we can also check in the discussion. Just a quick question about implementation, Matthew. Is there a software package available, or is it some?
No, so no, actually, so we are following this up. So in this paper we focus on the theory, but we now want to also maybe extend the theory also, but give maybe a package, or at least some like concrete implementation of the algorithm. So what I mentioned before are algorithms without covariates, and these have been implemented, and I'm sure there are packages out there. What we want to do is to bring these, bridge them, this type of algorithm also in the case of covariates, which I think is of interest. But yeah, it's work to be done.
Yeah, great. And just a general question about nonparametric Bayesian. So we always say nonparametric Bayesian, but that's a loud parameter.
So actually, what I like to call it more is infinite dimensional Bayesian, in the sense that the parameter is a function, so it's an element of an infinite dimensional vector space, or in general,
Great, thanks so much. If there is more question, we can have Matthew in the discussion as